energy minimization.
Thank you, Gabi, for the introduction, and thank you all for coming earlier to the talk. So I changed the title a little bit. Also, yeah, originally I was thinking only talk about one part, but now I will expand it a little bit. Especially I want to say this is a joint work with Egelby, who was my former PhD, and he was a postdoc in UCLA, and Professor Tony Chang, Wei Zhu from University of Alabama, and Jiming Duan from Nottingham. So originally, I was only thinking to talk about this part, segmentation with the elastic energy with convexity prior. But you see, after listening to quite a number of the talks in these few days, so I'm thinking to expand it also with this and also with something we have been doing recently. Especially, I should say, you see that I'm very inspired by the talk by Antonin, Laurent, and also Songhua yesterday. And the talk here is quite related with what they have been talking about. And also this part, I think, is very much related to something Yuri Boykov has been doing about convex priority. So let's start the talk about, you see, how do we, why we need the Elastica is essentially imaging smoothness. You have an image, and then you see, so which is a smooth? You have two surfaces. The image can be regarded as surface. You see that this is something very smooth we like, and this is something you don't like at all, right? But however, this is you view those two functions as a function, as a plot, as a surface. But if you view them as an image, this is the first image, and this is the second one. So you can see this is very smoothing, very pleasant. It doesn't have much meaning, right? But this one is, which is very terrible by looking here, but really has a lot of meaning. So therefore, you see that the general smoothness is especially the smoothness with revolving spaces, and this kind of smoothness is not good for imaging, because imaging, if you want to have a meaning, you must have a discontinuity, you must have variations. So, and then what's a way to measure the smoothness of an image? And especially here, you see under this surface, we plot the level contours. And then you see by looking at the level contours, you can see that this surface is a linear image. But looking at the surface, you don't see nothing. So therefore, the level contours are somehow very important for images. And so therefore, you see that we can measure the smoothness and the regularity of an image, something based on level contours. And especially you see that if we add a little bit noise, and then this is the surface, but the level contours, you can still see this is a linear image. So therefore, we are going to measure the smoothness based on the level contours. So the first one is the level contour for every given C. This is level contour. You see, for image processing, mostly C is from 0 to 155. But if you think of the continuous, let's say C is from 0 to infinity. And then you see that you measure the length of this contour and then sum over all the lengths. So this is one way. You see, you measure the length. You see, once you add a little noise here, and then the level curve becomes very oscillatory, the length increases dramatically. So therefore, if this is small, and then you will kill those oscillations. And then by the easy co-area formula, you see that you sum all the lengths together, this will give you the total variation. So therefore, essentially, the ROF model is just, you see, measure the regularity of image through the length of the level contours. So I think you see length, you have a curve, oscillatory will have a high length. But you see a curve with a smaller length or may not be oscillatory, but may not be smooth. So therefore, if you want the smoothness of the curve, and then we come to the Elastica. So here, A times the ds, this will give the, for curve, for arbitrary curve, ux equal to c, and the Elastica energy is the integration, here I miss a c, gamma c A plus b curvature ds. So if a b equal to 0, this is length, and then here the curvature square will measure, what the bending energy. So therefore, you see this is another way to measure the regularity of the curves. And we know that for the level curves, the curvature equal to this one. So therefore, you see that per curve, the Elastica energy equal to this one, plus put this one in, and then again use the co-area formula. So this is the one way to measure the regularity of all the curves, but plusing the Elastica energy. So this is another way to measure the regularity of a curve, of an image. So a third way to measure the regularity of the image is that you regard this image as a 3D manifold. You can calculate the Gauss mean curvature at each point, and then you see that this is the formula for the Gauss mean curvature. So and then you measure the regularity of the image by measuring the Gauss mean curvature of this one. You minimize this one, and this is you see the idea come much earlier from Niels Sohen and Kimo, and I think one more person was in the paper. So in this way, we can see that there are different ways to measure the regularity of an image. And so here, you see this, if you use that lens, and then you see just if we use the idea for image denoising, so this is the data fidelity. Here is a regularizer. If you measure the lens, it will essentially come to total variation. If you measure the Elastica, especially you notice P here, P equal to 2 or equal to 1, and this is measure the Elastica of all the curves. If you measure the mean curvature, so here will be the regularizer. Here we put the P equal to 1 or equal to the most, we use the P equal to 1. And then you can see that ROF is first order, and this is second order extension. In fact, this is also second order. The first order variance, you just measure the area of the surface. So here are the two first order ones, and those are the corresponding second order ones. So in this way, you see that you can use a higher order to measure the regularity of the functions. And here we just put this one for image denoising. If you modify this part, you can use for inpainting, restoration, zooming, or you can use a different regularization. I should say that all those ideas has been explored or touched in the literature by many people. You see, RF we know very well, and this one is mostly we know from the work by Masno and Morel, and also yesterday Songhua gave a very, very good introduction about those things. I know you see also Freddie Brookstein really likes the Elastica very much. You see he talked about those things very earlier. Here I'm listing, you see only a number of people. I think this is just a small portion of people you see who have been working on this one, and there are many more. I think as Songhua said yesterday, nearly everyone sitting here may have been working with the Elastica somehow. And also Antonian gave a very good talk earlier. I think it's somehow related to this one. Also, Songhua explained, you see, yesterday, if you use the gradient flow, you need to calculate the variation, the Euler Lagrangian equation, and then this is very complicated. If you use traditional methods, this will be very difficult to solve. Also, you see, if you use the mean curvature, this is also, you see, you can calculate gradient flow, getting the Euler Lagrangian equation is the gradient flow, and this is also very difficult to solve due to nonlinearity, and this is fourth order. This fourth order, nonlinear, very strongly nonlinear fourth order, very singular. Also, you see, in the literature, there are also quite some methods, and also you see Antonian lists quite a number of approaches in the literature. Here also I'm pointing to some of them, not all of them. Also, you see, I'm trying to say that in the literature, there are two different ways to deal with the curvature. So one, I would say, is called discretized curvature. So which means you have a grid, and then on the grid, you define something like a curvature. You see, like curvature equal to d theta ds. So on the grid, you can define the d theta ds in the grid, and then you see mimic the curvature thing. And this could give you some. Okay, thank you. Yeah, so in this way, you see that you can minimize or handle the curvature by some linear program and some fast algorithm. So there's another way to deal with the curvature is you don't define the curvature on a grid. So essentially, you give a function, you define the curvature in a continuous way. You have a continuous curvature, and then you minimize. You get Lagrangian, you get nonlinear PDE, and then you solve the nonlinear PDE by some kind of a discretization. So those two approaches seemingly you see very similar, but in practice is rather different. It's quite different things. And especially, I would like to say, you see that recently using operator splitting methods. You see, operator splitting is the Lagrangian EDMM. So those are all you see disguised. You see something you see very special cases of operator splitting. So use operator splitting, and then recently, as quite a number of people have been trying to get fast algorithm for those problems. I'm sorry, so it's, yeah, so we don't touch it once it works. Yeah, so I think there's quite a number of things. So yesterday, you see that Songhua already said about, you see, what's the algorithm we're going to use. So essentially, the algorithm we're going to use is that, she already gave a very good introduction. It's essentially like you minimize this image. Here is, and then we just introduce two variables, p equal to this one, n is equal to p divided by normal of t is a gradient over the L2 normal gradient. You introduce those ones, and then you expand the minimization variable u, p, n. So it's 5. It's 5 dimensions. So gradient by 2 dimensions, and here 2 dimensions, 5 dimensions. And then the minimization can be written in such a way. So it increases the number of auxiliaries. You just need to handle those constraints. So this is very simple linear constraints, and this is a little more complicated. So and then you can just discretize, put those into constraints, and use any kind of minimization code to solve it. And then how do you solve it? Mostly use alternating minimization. You fix 2 of them, minimize 1 of them. And then you see that if you fix p and n, this is a linear constraints, and this doesn't think, and then you can see u is a square here, and you minimize square with linear constraints. It's something very easy to solve. If you fix u and n, you solve a p. So here you see that p equal to this one. Mostly you put as you see, it's not exactly satisfied, or you put as a penalization something. You solve p, and then you see here L1. Here is a constraint. Mostly p is you can solve it by some simple threshold, and also n you get a quadratic nonlinear partial differential equation. So all the subproblems become very, very easy to solve, and by increasing those things. So this is essentially just by introducing those auxiliary variables, then you can easily get, you see, the subproblem very easy to solve. And so there's another way you see that these constraints, you can easily write the equivalent in such a way if you add this constant p equal to n. So therefore, we found out, you see, instead of imposing the 2 constants earlier, so we can impose this one plus this one plus this one. Those constraints are simple, even simpler than the previous one to solve. This is mostly the algorithm we have been using. So essentially, the original Elastica can be written in this way, and those 3 constraints. So you can use arbitrary, you see, a minimization code to solve it. But what we do, you see, we use a Glowinski's Augmented Lagrangian. So essentially, we deal with this constraint by penalization. We deal with this constraint. There is a difference. You see, here we use L2 penalization. Here we use L1 penalization. And then you see we use alternating minimization. So each of the variable, you fix the other 2, minimize 1 of them, and then updating the Lagrangian by gradient ascent. In this way, you see all the subproblems very easy to solve. You can easily buy FFT, or it's just simple threshold. And this is, you see, that getting an algorithm which is very simple to implement and very fast to converge. Mostly just use a few hundred iterations. Per iteration, you just need to solve some Laplace equation or threshold. So it's very, very easy. So also, you see, Songhua gave a very good talk about this one. Also, she has a very much better method than this one, as she was talking about. Also, I should say that there's a number of approaches recently, and which is also following this direction. I think, yeah, this is not, but I think a number of those one, include Professor Xue-Cheng, has been extending this one, getting quite fast and numerical algorithms. Also, you see that you can use the same idea for this mean curvature minimization, even for the minimum surface area minimization. So essentially, you see that this p, you get ux, uy, just put the constant 1 here. You can also solve this one by very fast methods. Glowinski come up with a new idea such that he just directly impose this one, and all the subproblems he get very explicit solution formulas, which also very, very fast. I think this is everyone knows about it. So you have a noisy image. If you use a TV, you minimize the length. You see that all the oscillation disappear, but the curve are not so smooth. But if you use Elastica, the curve will be very smooth and the image looks much more beautiful. And this is expected, everyone knows about it. You see, we have been using it for all those things. Songhua also use their algorithms for those things. And for denoising, you see for denoising, really you see just a number of seconds. It's very, very fast. We also use it for zooming. So you have this one used for zooming. And then you see that it's just changing the fidelity term. So that part is something, it's not new. Also, Songhua gave a very good introduction yesterday. So now the second part I'm going to talk is that we just use this idea for image segmentation. So image segmentation, you see that we just, we don't want to do something so fancy. So essentially, the original convex model using the level set. So here, phi is the level set, C1, C2 are two constants. So you segment the image, given image F into two regions, one region close to C1, another region close to C2. You don't know C1, C2, you don't know the interface, so therefore you compute this level set function. So essentially, you are trying to approximate this F function by a piecewise constant function of two values regularized with a length. So this is essentially the convex model. And then instead of doing that one, also I think several people talk about this one. If we don't regularize the length, let's replace this regularization by the Elastica of the interface, of the boundary of the segment image. And then you see that and then if you use a level set, so you will need to solve F minus FC and plus this one, and here is a P. We are talking about P equal to 1 or 2, and here is a level set function. If you do this simple change, we have given examples, especially P equal to 1, P equal to 2, it seems there are crucial differences. And so if you take a P equal to 1, so here P equal to 1 here, and then you can allow your segmentation images to have corners. But if you take a P equal to 2, and then your segmentation, you will not be allowed to have corners. So the curve must be very, very smooth. And also, if a B equal to 0, this is essentially reducing to the convex model. We can show that B equal to 0, as also you see Songhua talking about, or several other people talking about. If you do segmentation, you see the broken part, you will not be connected. But you see that for the Elastica, we show that no matter how big is the gap of the broken part, if you just take the ratio between A and B properly, you can always connect the broken parts. And this is given. And also the ratio between A and B determines which scale of the region will be retained. So if the ratio differs, the different scale from the image will disappear or will retain. And especially where the one thing so if you take a B very, very big, if you do this segmentation, and then your segmented region will be convex, will be convex. And especially I think this is point I will try to explain more. So mostly we are giving this one by examples. So one of the example I think in this paper is that if this is the input image, F equal to 0 here, 1 here, and then if you really the length and depends on this gap and the width. If the gap is bigger than the width, the TV will give the broken part. But we can show that if you use the Elasticas, no matter how big is this gap, if you just take a B, the ratio between B properly, you can always connect this one, no matter how big, how far away they are. If you just take the ratio between those two, and this was given as an example. And here is also, you see that, I think here is the example, right? We construct the analytical solution and show that if a B and the ratio and B and A are proper enough, and we show where the exact solution of that minimization problem always connect those two parts. So this is the connecting part. There's another one, you see that if no matter B equal to 1, P equal to 1 or 2, if you just keep the ratio, and you see like these two circles, and we can show that for smaller B, all those two circles both will be there. If you increase it to some value, the small circle will disappear. If you increase again, the big circle will disappear. So the ratio between A and B also determines which scale of the object you will keep in your minimization. And then the next thing I'm going to talk about is convexity. I think convexity, and especially I think Euler has paid a lot of attention. He did something very nice. And also you see that in the literature, and many people have noticed that when you do segmentation, you see many of the real objects are convex. But when you segment, so you cannot guarantee. If the input image is very noisy, so you see like ultrasound, if you segment the heart, you may get many pieces. You don't get a single convex object. So how do you guarantee that your segmented object is a single convex object, and how do you do it? I think is a number of people have been doing this one, especially I think this seems to be the first one who give a way to do it. So this is how do we try to guarantee the convexity. So we use a simple theorem from differential geometry. So in differential geometry, if you have a simple curve, you calculate the curvature of this curve. Here, notice you don't put a square, you put p equal to 1. And then curvature is a turning of a theta. If you have such an image, when theta goes around, and d theta is exactly changing 2 pi. So therefore, you see, for arbitrary curve, you put the absolute value here, and the curvature integration will be always bigger than 2 pi. If equal to 2 pi, if this region is convex, arbitrary convex region, this will be positive. You integrate equal to 2 pi. So therefore, the integration of the curvature attains the minimum. The minimum is 2 pi for arbitrary convex region. No matter your region is so big or so big, if it's a convex, simple, and this will you see equal to 2 pi, equal to pi. So this is what we use for segmentation. So essentially, you see that if you take this b very, very big, and then that's essentially you are trying to, so notice we put the p equal to 1 here. And then that's essentially you're trying to minimize the curvature integral on the curve, right? And the other part is that you can just say they are constraints or something. So therefore, when b is very, very big, this curvature integral will be minimized somehow, or be getting closer and closer to the minimum. So once you're getting closer and closer to the minimum, and then you can guarantee, you see, that in the end, and your region will be convex. So this is essentially how do we try to guarantee convexity. So when b is getting bigger, but especially the ratio is getting bigger and bigger, and this integral is getting smaller and smaller, and smallest value is 2 pi. You're getting smaller and smaller, and then you see that you'll come to a convex region. And this is also something very interesting. You see that mostly you see that we use this one as a regularizer for image processing. You put the p here. So this thing shows that once p equal to 1, once the curve is convex, there's no regularization effect. Arbitrary convex region will give this one. So this also shows the crucial differences between p equal to 1 and p equal to 2. So p equal to 2, so here you see the arbitrary curve. If you minimize this one, p equal to 2, and then the curve will become smooth and smooth shrunk to 0. But if p equal to 1, once it becomes convex, and this term have no effect. This term have no effect. So therefore, you see that the Elastica regularization, there is a crucial difference if you put equal to p or equal to 1 here. And we also have some examples in the paper. So this is essentially the central idea. We use a curvature to incorporate the convexity prior. So here is numerically how do we solve it? We have used 2 ways. So one way is that you have so originally you use a 0, 1, but we relate to an interval 0, 1. Here is the data term. Here is a curvature. We don't have a 0. You see that once you relax, this is still, you see that still produce what kind of relation with the curve of the curvature. We don't have exact proof, but numerically we verify it. The other way is that we just use a level set. So use a level set, and then we still use the same idea. So essentially we introduce a p equal to this one, n equal to this one, and then there is the fast algorithm, which is I talked about in the beginning. You can use it to solve this level set minimization. You get the level set fast solver. The idea is very similar, but the details, you need to go through all the details. You can still, even though you don't use the traditional way to solve this level set one, so you still use the Augmented Lagrangian, and P equal to this one, A equal to that one. I can't remember, do we introduce a U equal to Heaviside or not? Just you see, by introduce proper auxiliary variables, you don't use the traditional time marching to solve the level side equation. And use the Augmented Lagrangian or ADMM to solve the level side equation. You can solve this one very, very fast, very, very fast. Yeah, so you can use Augmented Lagrangian or ADM to get very fast solvers. Here is the experiment. So you input, you see that 2 small circle, 2 big square plus this one. Here is, if we take the B small enough, you can see all the region come in. If you increase to some value, this is, you see, we have one example, is just shows 2 circles. We don't, in the example, this is not included, but the 2 circles, we show that B with a proper scale. So you can see the smallest scale disappear. And then if you increase on the biggest scale, and then the other. And so it seems that this, compared with the TV, we believe that you have a better scale selection than the TV. But we don't have a theory, but we have examples to show this one. So that's a scale selection with the Elastica energy. This one I think is we are just trying to show you that if you don't use if you use a length term to segment these kind of very thin structures, so you will get many broken parts. But if you use Elastica, you will always get connected, and especially if you choose a B properly. And you see that if you are very far away, you need to increase the B and then to get them connected. So this is, you see that to connect a broken part. Here is about the convexity. You see, this is the input image. You have different scales. You have you see that different convexities. And then if you take a B very, very small, so this one is this is non-convex. You can see it's a little bit convexified, also a little bit convexified. Then you see if you increase one, and then this is, I think this is scale 2 oscillatory, so this scale already out. Only the remaining are here, and this is getting more convex. If you increase more, you see that those 2 scale, and then you see, you also get more convex. So also you have a scale selection plus that the region are very, very convex, getting more and more convex. Here is the input image. You see that you want to get the head, and this part is occluded. So and then you see if you take the ratio, you can see the ratio is very big. If you take the ratio is big enough, and then you will get a single convex region. And then I also show you see that. Also show you see that if the ratio is not big enough, you see you get it, but the convexity is less. And then if you increase the bigger, you get more convex, and then in the end you get very, very convexity. So this is you see that this ratio determines. I should say that at the moment we are testing another method which is very much related to this idea and produces something which is even better than here. The algorithm is more stable. So this is. Related to the convexity. Also here you see that if you take a B smaller, you will get you see the region will be non-convex, capture more region. Once you increase the B and more, you only get the convex. So it's when B is getting bigger, it promotes convexity. So now I'm coming to the last part of the talk. This is something which is very, very new, and then probably I'm not so detailed about this part. So this is, we are trying to solve, you see that you try to minimize the curvature of a region with something which is very fast algorithm. So essentially you see that we try to minimize this one. So here we use a level set representation. So here this part will be the Euler Elastica for the curvature. For the curvature, Euler is for the interface. So here you see that could be the region force, as Lauren Cohen talked about. Here be the region force. So essentially you see this model, so we are aiming on segmentation, but you see the other things you can do it in a similarly. So you want to solve this one. So the method we use now is introduce a P equal to this one, N equal to this one, and then probably we also use a U equal to Heaviside phi and then you increase the unknowns, and then you use a constraint minimization to solve it. You get fast algorithm. So the new method here, we found out this was just through some test. We found out this is really very fast. This is what we do. So we introduce U is equal to Heaviside, and the G phi is equal to this part. Here I put the P equal to square, but P equal to arbitrary, 0, 1. So G is equal to this one. And then you see that if you do this one, and then you can see that the minimization, which was originally here, your G phi, the curvature will be the elastic curvature will be here. So here U become gradient U, and then here you have a U, and U is, in this case, U is a binary variable, and phi is a distant function. So therefore satisfy this one. So and then you see that this new minimization, you need to minimize a binary variable, you minimize a level set function. So yeah, so again you see that we do alternating minimization. If phi is given, and then you can easily calculate this part through this formula by very, very quick, you see, standard discretization. And so this part is known. And then you have a U, and here you have a U here, have this constraint, you minimize this U. So therefore, we know from the Acetoglu-Nikolova-Chang, and then we know that you can relax this one to be interval, and this becomes, you see, convex. So this is essentially you solve the convex constraint in RLF model. And then there are many fast solver, use Chambeau-Porc, Augmented Lagrangian, and many other. You can solve this one very, very fast. So that's if you know the phi. But on the other hand, if you know U is a 0, 1 in a region, 0 outside, if you know U, and then we see that already through these constraints, you have a uniquely level set. Because you already define the interface, and phi is a distant function. So you know the interface, you know this constraint, you easily get the level set function. So therefore, you see that using this one, it seems that to minimize that energy, so you give a U and a corresponding level set function. And this one, we just use fast marching or fast sweeping, anything. There are many software, even MATLAB, there are ready software to solve this one. And then once phi is given, then you need to minimize with U by this one. But what we notice, you see that you need to add a gradient flow-like thing to slow down the evolution. In this way, you see, you're just alternating between those two steps. And then this one is very fast. You solve RLF, and this one you just you see the redistancing. You just between those two, and it seems the convergence is very quick. Normally, just take about not more than 100 iterations, you get solution. This is very easy to solve very fast, and this is very easy. So the whole algorithm becomes so simple, right? So you just have an RLF solver. You can minimize the elastic curvature. This is really something. It's easy to do. And quick to compute. Yeah, so this is, so we test on this algorithm. Really the performance is really super. We don't believe it, really super. So essentially, so here we use it for segmentation. So here is the input image. Here if you use a proper B, and this will be segmented. And if you use this one, here will be segmented. You can see that all the broken parts are connected. What we do is, essentially, here is the evolution of the iteration. So what we do is we set B equal to 0. And then you just need to solve RLF solver, and then you see just third iteration, you get it. We use that one as the initial value. And then you can see all the parts are broken, and then put in B in. Put the B as the iteration goes, and you can see that all the broken parts are getting connected. And the whole process is the iteration. I think this one, I think maybe 20, 30 iteration, you already get it. Very, very fast, very fast. Here is a corresponding level set. So here is a level set, and also you get the binary. So there's a binary function, and there's a distant level set function. You just switch between them, switching them. And this is really very, very quick. Yeah, so here for this example, again, we see in the beginning we set B equal to 0. And you see all the broken parts are here. And then you see, and then you set a fixed B, and you do the iteration, and you can see the broken part are getting more connected. So in the end, this is level set, and this is the corresponding contour. And the whole thing is very fast, and the implementation is very easy. We also use the test on this one. Yeah?
Wouldn't you get the same result with a simple Tranvese algorithm?
No, this is Tranvese. So if you use Tranvese, you get this one. This is, if you put the B, you get this one. That's you connect this one. So therefore, if a B is very small, you see some part you may connect here, but you may it depends on B. So B, when B is bigger, you can connect. No matter how big is the gap, you can connect it if you take a B properly. But because this one is so fast, we can easily modify the B. So here we also use the inbending. I think this example, Antonin talk about it, or Songhua talk about. So essentially, you take a part of the circle away, you minimize it, try to see if you get a circle or not. So we take about nearly a quarter. Even we have been testing, if you take about maybe 70% of this one, you don't get a circle, but you get something like a mushroom or something, right? Here you take a small part. You see, this is a standard test. We also try on the Knitzhard's triangle. This is a Weiker's rabbit, but it's a different rabbit. So essentially, some handwriting, you destroy about 80–90% of it. You just leave a small part, you minimize, you get this one. We also try this one on real document. If you really have a real handwriting document, you destroy about 80–90%. You minimize this one, you recover document quite well. So this is very similar to what Antonin talked about. Weiker's rabbit is a similar thing. So especially when we saw this one was very surprised. And this was very fast. So you don't take much time. Very fast. This is the thing Songhua was talking about yesterday. So we use exactly their model. I think this model was published in the paper by Kangsen Zhu in the Simon Imaging. This is published. So essentially, you see that. So here, the label in the Q region is known, and then you see we also use their corner diffusion. So therefore, you only need to find the value. You found that u is equal to 1 here, 0 outside, and then you minimize the curvature of this interface. So So we compare this curvature. You see, minimize this curvature by exactly the way we did. So during the computation, so we exclude these regions, the Q region from the computation. The computer region is only this one plus this one, but exclude this one. So we exclude the region, and we still use, you see that RF in this exclude region, and the level set everything we do it. And this is, you see that the minimization. You can see that you recover this circle, also you recover this triangle. But when we test on this one, so we really believe, you see, the method is correct and fast. It's really very fast and very simple. So, yeah. And then you see that I think most of the old ideas about turning the constraint. I'm sorry, you see that here I'm listing. So in the beginning, I listed a number of other papers. I think I saw a number of new papers coming out. So the idea the curvature regularity was from Tony and Zhu. And this is here we introduced this constraint operator, constraint minimization for the Elastica. Then a number of things are coming later, especially the newest algorithm was tested here. It turns out really very fast. So, yeah, so that's all. I thank you. So I'm happy to answer your questions because you see, Elastica seems to be something most of you, or nearly everyone of you, has been thinking about. Thank you.
Are there some questions?
I understand that when you use p equal to 1, you have better preservation of corners.
Yes.
But am I right that you treat convex and concave corners in different ways? So you better preserve convex corners and you somehow do not preserve concave ones?
So your question that...
because of the property of the curvature.
Yeah. So if it's convex corner, if you calculate the curvature integration on the curve, you get 2 pi. If you concave, and then you get more than 2 pi.
Right,
So.
and you would like to minimize that.
Yeah, you like to minimize it, so therefore you punish concave, and then it will become convex.
So does it mean that it could be better to consider instead of curvatures a gradient of the normal?
The gradient of a normal, that's essentially the curvature.
No, curvature is divergence.
Oh yeah. Oh, yeah. The gradient of the, so that's you are using essentially the Hessian forbidden norm. The forbidden norm of a Hessian metric. So that's a different thing. That's also, I think, yesterday why Johan asked about Songhua about that one. So you can use the diffusive. You see you have the Hessian, and then you see like anisotropic diffusion with the second order. You can do something similar. But in fact, we tried. We compare, you see, Ixen, Johan Weikert's idea about anisotropic diffusion to second order and do something similar. It seems that Elastica still, if the gap is bigger, Elastica is better than using the second order. Yeah, I think we tested about that one also, especially one of the guys. So he compare. He has another publication about it. Yeah. Oh, Johan.
So I think there is some subtle, not subtle difference in terms of what happens as you change B in terms of how you enforce convexity. I understand the 2 pi argument, but like if you may have multiple objects which are convex, but this is not a convex shape. So some of you see what I mean, right?
Yeah.
So indirectly, yes, each of them. So it's slightly different from just enforcing convex, because like convexity is a global constraint, while you enforce it while local property of curvature. So I see how it's related, but it's not exactly convex.
Exactly, I fully agree. Right.
I have just 2 remarks which do not only refer to your talk but also to some other talks. Let me tell you 2 secrets. The first secret is I have never used a rabbit in any of my publications. There is no Weikert's rabbit.
Ask Antoni.
It is a cat.
Why is a Weikert rabbit?
Also, it's becoming a running gag. It's a cat. The second story is there was regularization before Rudin Otter-Fatemi. Believe it or not, it is true. There are, for instance, people like Nordström who did regularization in 1990. And it's not necessary, if you regularize an image, to use a non-differentiable regularizer. There is no theory which supports that. There are also other alternatives, and ignoring those people in the references is simply unfair.
Yeah.
I have looked at your segmentation model again. There's some mystery. It's fine.
Yeah, this is a segmentation model.
Yeah. So my question is, you see in this model, you have the Euler Elastica is somehow in between Elastica and the TV or something. It's in between. This
B equal to 0 is the TV. Once you have a B, and this will be this is the curvature P.
Yeah, but later on this is Elastica, but you don't use this one. You replace gradient phi by gradient H phi. So then it's like a mixture between the two or something.
Oh, it's the same. It's the same.
Why it's the same?
If you put here H phi and here H phi, it will be the same.
I see.
Yeah, it's the same. Because H phi is you get delta, the delta cancels. It's the same. So this will give you the Elastica for the interface.
Magic there. Okay.
Yeah, I think that was even explained in the. I think that was explained somehow. So those 2 models, I think we give we give an explanation. I think about your question about the delta phi. I think. Oh, it's very slow. Oh, sorry. That was something different. This is Roland, this is his wife, this is the Bob. Yeah. So I think we explained about the point you asked about in one of the paper with Ron Kloswinski, which I referred in the last slides. Yeah.
So, are there some more questions? No, thanks, speaker again, and go ahead.